Hello and welcome to the chapter 14.1 learning video on lengths of curves. At the end of this, we will be going over this most missed one from the 14.2 homework. Feel free to skip ahead if you want to see that first. So in Calculus 2, you saw the arc length of curves, and this is a generalization of that to vector-valued functions. So recall the idea from Calculus 2, where if you want to find, say, the length of this curve, then you can think of it in the following way. You have your delta x and your delta y, and these form a right triangle. And then you have this length of the hypotenuse, delta s, the change in the length of, well, the curve. And as delta x and delta y approach 0, then this hypotenuse will greater and greater lie tangent to the curve. And as we know from the Pythagorean theorem, delta s squared is equal to delta x squared plus delta y squared. So therefore, delta s is the square root of delta x squared plus delta y squared. But this is a delta s, the change in s, and what we want to do is add all of those together. And that means integrating. After all, the integral sign, you know its etymology? Integral sign is an elongated s for sum. So we add all of those together. And the arc length is thus the integral of the square root of delta x squared plus delta y squared. Okay, but d what? Okay, well, it doesn't really make sense in this context, or as written, I should say. However, what we can do is rearrange this in the following way. And that way it was as follows. So we had this d what? What does that mean? Okay, well, we can do the following thing. We'll multiply this by a delta x on the outside, and then this becomes 1 plus delta y over delta x squared on the inside. To see that, well, distribute that delta x inside of the square root, it becomes delta x squared. So then I have a delta x squared there, and delta x squared over delta x squared there cancels out. So it's the same thing as that. This is a bit of abuse of notation. In reality, we're taking the limit, and we replace each of these with our infinitesimal version, and it becomes this. That was the derivation of the arc length formula in Calculus 2. And that was the arc length formula for the arc length between a point A and B. Now, with the vector valued function, it's exactly the same derivation. And what we wind up with is this. And by exactly the same, I mean, we'll end up having here our integral of the square root of delta f squared plus delta y squared, delta g squared, plus delta h squared. For the magnitude, essentially. The Pythagorean theorem generalized into 3 dimensions, as we saw back in chapter 13.2. And then what we can do is divide each of these on the inside by a delta t. And we need to not do anything fundamentally. So that's dividing by a delta t squared on the inside, that's squared. So then we need to multiply by a delta t on the outside, and then we don't do anything. And delta f over delta t, that's df dt squared. Similarly, delta g over delta t in the limit, that's dg dt squared, and delta h over delta t, that's dh dt squared. Okay, all dt between our 2 points a and b, corresponding to the bounds on the parameter t. And that guy is this, f prime, that just means df dt. So this really is a direct generalization of the calculus 2 arc length, and hopefully that makes sense where it comes from. It's just applying that Pythagorean theorem and integrating all of those little delta s's over the length of the curve between our a and b bounds on our parameter t. So square root of the sum of the squares of the derivatives. But notice that in as much as, well, r of t is f g h, and thus r prime of t consists of the derivatives of these guys. Then this whole guy, the square root of the sum of the squares of the components, is by definition the magnitude of r prime of t. Okay, but this guy, what is that? That's speed, as we learned in 14.2, 14.30. So another way of thinking about arc length is that it is the integral of speed, not of velocity, of speed. And after all, speed, that's change in, well, velocity is the change in displacement over the change of time. And speed is the change in the magnitude of displacement over the change in time. So if you integrate that with respect to time, then you wind up with just the change in magnitude. And that change in magnitude, adding up all of those little changes in magnitude over the entire curve, that winds you up with the length of it. Imagine a bunch of, little changes in magnitude, and you add all of those little changes in magnitude together, and you wind up with the length. Like a chain link, like a chain that you're straightening out. Each little chain link is a change in magnitude. So let's do an example. Let's find the circumference of a circle. So we all know that is 2 pi r, but now let's do it just as an example using our arc length formula. So we know that the circle is parameterized. The unit circle is parameterized by cosine t sine t. And we know that the length is the integral from a to b of f prime t squared plus g prime t squared dt. Okay, and in this case, that is our f of t, that is our g of t. And what are our bounds? So this will be between t equals what and what? Well, it's 1 full revolution. That corresponds to t equals 0 to t equals 2 pi is 1 full revolution. So the length is the integral from 0 to 2 pi of the square root of, okay, so derivative of cosine, that's negative sine. And derivative of sine, that's cosine. Okay, but sine squared plus cosine squared is as usual equal to 1. The minus sine squared goes away. That's by the usual Pythagorean identity. So we have the integral from 0 to 2 pi of 1 dt. And that is t integrated from 0 to 2 pi. Integral of 1 is t. And that is 2 pi. And indeed, that corresponds to our 2 pi r. In this case, the radius is 1. So 2 pi r is 2 pi times 1 is 2 pi. So that's actually a very slick derivation of the circumference formula using arc length. And we can generalize this to other shapes. So for example, an ellipse, we know that the formula for an ellipse looks like this. Notice that this is of the form x squared over 2 squared plus y squared over 1 squared is 1. So the color code, this would correspond to the x-axis being 2 and the y-axis being 1 in this case. So what is the circumference of this ellipse? Well, the first thing that we need to do this, applying our arc length formula, is parameterize it. And recall from an earlier section that a parameterization of this is r of t is 2 cosine t sine t. We did this in one of the chapter 13 sections. So one full revolution, just as with the circle, occurs between t equals 0 and t equals 2 pi. As an x begins at 2 cosine 0, that's 2. When t is pi over 2, then this guy goes to 0, that guy is 1. Now we're at a height of 1, etc. So dt. The circumference arc length is therefore the integral from 0 to 2 pi of the square root of the sum of the squares of the derivatives of those components up here. So d dt of 2 cosine t squared plus d dt of sine t squared. And that's this derivative of cosine is sine, derivative of, or negative sign rather, but the negative sign goes away under the square. And similarly, derivative of sine is cosine. And this integral actually cannot be evaluated. The indefinite integral cannot be evaluated in terms of sine, cosine, natural log, etc. However, it can still be numerically approximated, and we can numerically approximate this integral to be 9.688. So that would be the approximation to the circumference of this sphere. I mean, of this ellipse. And this gets at the point that often arc length cannot be precisely, well, it can be precisely expressed in terms of an integral, a definite integral, but that definite integral may not necessarily be able to be precisely evaluated, and instead it may only be able to be numerically approximated. And that's fine, but in this class, naturally with our examples, they'll all be able to be evaluated precisely. No need to do numerical approximations to them. So let's do an example. This one will be able to evaluate it precisely. So we considered this ellipse in a previous section. I think it was 14.1. And actually this is not, well, it's a helix. This was cosine ti plus sine tj plus t over 2 pi k. This was the helix whose projection onto the xy plane is a circle, and which goes up by 1 unit every revolution. So let's find the length of this helix within 1 revolution, so between 0 and 2 pi. So in other words, it's finding this length that's beginning at t equals 0, going up to t equals 2 pi. And again, this picture has a 4 by the cosine, but it captures the idea. Just imagine that that's a circle in the projection, and we're going up by 2 pi, by 1, over difference of 2 pi and t. Okay, so we plug this into our formula for the arc length. The arc length is the integral of the square root of the sums of the squares of the derivatives, in this case from 0 to 2 pi. So we have d dt of cosine t squared plus d dt of sine t squared plus d dt of t over 2 pi squared all dt. Okay, so derivative of cosine is minus sine, and derivative of sine is cosine. And derivative of t over 2 pi, this is just a constant, 1 over 2 pi times t. And the derivative of a constant times t is just that constant. And the negative sign goes away in the squaring. This is the sine squared plus cosine squared. And as always, that is 1. So we have the integral from 0 to 2 pi of the square root of 1 plus 1 over, okay, 2 squared is 4, and pi squared is pi squared. 1 over 4 pi squared dt. Now, when you look at this, you might think, oh no, how do I do that? This is just a constant. And the integral of a constant, like the integral of 5, is just 5t plus c. Same thing here. This is just that constant, 1 plus 1 over 4 pi squared times t. And we are evaluating that between 0 and 2 pi. And that is 2 pi times the square root of 1 plus 1 over 4 pi squared. And that makes sense. If it were just a circle, it would be 2 pi in circumference, but this was a helix curving slightly up. That should make it a bit longer. And this term here is a bit over 1, so that makes it a bit longer than 2 pi. Now, we frequently want to use arc length as the parameter. And before we say exactly what this means, let's go through some reasoning. So we know from 14.3 that the speed is the magnitude of velocity. And we also know that velocity is the derivative of position, r prime. And the arc length of a curve from 0 to t is the integral from 0 to t of the speed dt. Remember that this first part here comes from this formula here. This whole thing, the integrand, is the square root of the sum of the squares of the components of r prime of t, as we saw. And thus arc length is the integral of speed. And thus, similarly, well, arc length is the integral of speed. So d dt of arc length is speed. And arc length as parameter occurs when the parameter t corresponds to arc length. And by corresponds, what we really mean is. So in other words, when the integral from 0 to t of the speed dt, remember that this formula is the arc length formula, is t. So i.e., but this is the same as saying that the speed, that integrand, is 1. The only way for, well, this to be the case for all t is if that integrand is 1, and thus the integral is just 1 times t, a value between 0 and t, yielding t. And this will be a key insight for reparameterizing curves to have arc length as the parameter. The idea will be to make the speed 1, and if the speed is 1, then the arc length is the parameter. Those are the same thing. Okay, and this is summarized here. Let R of t be a smooth curve. The arc length is given by this, as we know. We use S for the arc length. And S of t, the arc length up to t, beginning at a, is the integral from a to t of the speed, well, du in this case, they're using u as a parameter. And the speed is the magnitude of r prime, because r prime is v. And equivalently, thus, the derivative of arc length is speed. And thus, if the speed is 1, then the parameter t corresponds to arc length. That's really everything that we just saw here. So first, let's do an example verifying that something is an arc length parameter. First, intuitively, so as we go around the circle, it takes 2 pi. I mean, t needs to go between 0 and 2 pi to go fully around the circle. However, the circumference is also 2 pi. So what that means is that t is varying at the same rate as the change in arc length. So in other words, we're going around the circle at 1 unit per unit. 1 unit per change in unit of t, I should more clearly say. So the speed, in other words, is 1, and the arc length change is the parameter t. And we can verify this mathematically by just finding that the speed is 1. So to verify this, what we need to do is show that the speed is 1. Okay, well, the speed, magnitude of velocity, that is the magnitude of r prime of t dt, since velocity is derivative of position. And that is the magnitude of negative sine of t cosine t, which is the square root of negative sine t squared plus cosine t squared. And as always, that's 1. So we have the speed of 1. That is an arc length parameterization. Now, frequently we want to convert a parameterization to be of arc length parameterization. And converting a parameterization is known as reparameterization. And because parameterization by arc length occurs when the speed is 1, here's the idea. To reparameterize a curve by arc length, then if the speed is constant, we divide the position t by the speed to make it speed 1. So thus, we reparameterize with t equals s over the speed, full stop. So think of it this way. If you're moving around a curve, draw a picture. If you're moving around a curve at 5 units a second, like this, 5 units a second, what we want to do is make the speed 1 unit per second instead of 5 units per second. So what we do is we just divide by 5, and now we're going at 1/5 the speed, and thus we're now going at 1 unit per second instead of 5 units per second. We begin with 5 units a second, divide by 5 for the speed, and now we're going at 1 unit a second, which is an arc length parameterization, speed 1. So to do this, we first need to find the speed. So let's reparameterize this curve by arc length. First need to find the speed of this. That's the magnitude of the change in position over change in time. the derivative of this, the speed, the velocity, will be minus 3 sine t, 5 cosine t, minus 4 sine t. That's the velocity inside, and then the magnitude of that is the speed. The magnitude of that is that. Now, minus 3 squared is 9, minus 4 squared is 16, and we gather together the sine squared terms. So we have 9 plus 16 is 25 sine squared t, and here we have a 5 squared, we have a 25 cosine squared t. So that's 25 times sine squared plus cosine squared. And as always, that guy is 1. And the square root of 25 is 5. So that means that as t increases at a rate of 1 unit a second, then we're going around this curve, whatever it is. In fact, we earlier showed that this is a circle that is not parallel to any axial plane, and we're going around that curve at 5 units a second. And now what we want to do is slow that down by a factor of 5 to make us go at 1 unit a second. So that means replacing t with s over 5, and that will do the trick. I'll try to make my s's not look like 5s. So we replace t with s over 5, where s is a new parameter name. And we have r of s is equal to 3 cosine s over 5i plus 5 sine s over 5. Okay, hopefully you can tell my s's apart from 5's, j plus 4 cosine s over 5k. And that is now moving at a speed of 1. We have slowed it down by a factor of 5 from its initial speed of 5. So now you're moving at 1 unit a second, which is an arc length parameterization. So you try your hand. Here's a curve. Try reparameterizing this by arc length. I encourage you to pause the video, try your hand at it. We'll do it in a moment. Okay, so what we want is to slow it down by its speed, so that then its speed is 1. So first thing we need to do is find its speed. So its speed, that's the magnitude of velocity, which is r prime. Okay, derivative of 3t is 3. Derivative of 3 plus 2t is 2. And derivative of 1 plus 6t is 6. Okay, and we have the square root of 9 squared plus 4 squared plus 6 squared is 49. Okay, so 7 is the speed. So as we are moving along this curve, which you may recognize this is actually just a straight line, we're moving along it at 7 units a second. And for an arc length parameterization, we want its speed to be 1 unit a second. So what we want to do is replace that parameter with something 1/7 as fast. So we replace t with s over 7. And our arc length parameterization is r of s is 3 times s over 7 t, or not t, I know my s's might look like phi's. Remember, that's an s, our new parameter name. Plus 3 plus 2 times s over 7, replacing t with s over 7j, plus 1 plus 6 times s over 7k. And we can simplify that a bit if we want, but that's it. That is our arc length parameterization. Remember that we use s for arc length. That's why we choose this variable name for our new variable, our new parameter. Now, many curves, they may be moving with non-constant speed. And everything I'm about to show you, you don't need to use mathematically. I just want to illustrate that it is always possible to reparameterize such that the speed is 1. It's just that if the speed is non-constant to begin with, then you'll often wind up with the non-integrable function, or even if you do, it'll be the inverse of a non-integrable function. However, many of the things that we'll be doing will require an arc length parameterization, and I just want to show that it's always possible in theory, and that always being possible in theory is necessary for the mathematical underpinnings of what we'll be doing. So in general, to reparameterize a smooth vector function r of t by arc length, well, we want to find another parameter s, which we can think of as f of t. F is like our change of parameter function. For some function f, so that the speed of this new parameterization, the magnitude of v of s, is 1. So that now we are moving at 1 unit a second instead of whatever v of t moved at. And we can do some derivations, but the point is that s is still the arc length, and that's the integral from 0 to t of the magnitude of velocity, which is just the speed, dt. So that's really our original definition of arc length, and that's our arc length parameter as well, since we're reparameterizing by arc length. But s is f of t, so what that means is that f of t is this guy. But now to replace our t with an s, well, from this, that means that t is f inverse of s. So we would need to replace t in the original parameterization with f inverse of s, where f is this integral of a magnitude, and that magnitude involves the square root of sum of squares. So not only are we taking the integral of the square root of sum of squares, but then we're taking the inverse function of that. And the point is that that can almost never be found in terms of elementary functions. It needs to be done computationally, but it still exists in theory, certainly. I mean, that's the formula for it. And that's really all there is to our short 14.4 arc length chapter. Again, you don't need to actually know this part. It's just showing that in theory, arc length parameterizations always exist. In practice, it will always be something like this, where it's of a constant speed to begin with, in which case it's quite direct to reparameterize by arc length. You just find that speed and then replace t with s over that speed to slow it down and make you move at 1 unit a second. So now, as promised, let's do this 14.2 problem. Consider this parabola. First, why is this a parabola before we even keep reading? So we can think of this guy, well, it is our x, not just think of that is our y. And in as much as y is t, that means that we now have that x is equal to a y squared plus, and that's a parabola. It's that direct. Y is t, so x is a times y squared plus 1. And this is a sideways facing parabola. So it'll look something like this. Okay, now we want to find all points where r and r prime are orthogonal. We know in general that vectors v and w are orthogonal if and only if v dot w is 0. So this problem means that we want to find where r dot r prime is 0. Okay, so we want that r dot r prime is 0. Okay, well, r is a t squared plus 1, comma t. And we want to take the dot product of that with r prime. Derivative of this is 2a t, comma 1. We want that be equal to 0. Okay, so this is 2at times a t squared plus 1 plus t, taking the dot product. And I suspect that this might be where some people got tripped up. They might have distributed this and gotten a t cubed. And how do you deal with the t cubed? Well, instead of going that route, let's realize that we can factor out a t right here. So this is t times 2a squared t squared plus 2a plus 1 equals 0. And that way we have just a product of two things. One is a t, the other is a quadratic. Much nicer. And we know that a product of two things, so let me use different variables. We know that in general, if bc equals 0, that means that either b is 0 or c is 0. If a product of two things is 0, then one of them is 0. So from this, we can therefore conclude that either t is 0 or the other guy, 2a squared t squared plus 2a plus 1 is 0. In the second case, then solving for t, that would mean that t is equal to the square root of negative 2a plus 1 all over 2a squared. It's all under the square root sign. Moving that to the other side, dividing by 2a squared and taking the square root. Okay, that looks very ugly. Now, we were told that a is a positive number. Because a is positive, if a is positive, then 2a plus 1 is positive, and also 2a squared is automatically positive. So we know that this box guy is positive. But we have a negative sign. So therefore, we know that this is a negative number. And we're taking the square root of a negative. So therefore, in this case, t is imaginary. So that's a non-solution. It's not on the parabola, unless we're dealing with complex calculus on the complex plane. We're not doing that. So we just throw that away just as we would in any previous calculus class. And our only solution that's real is t equals 0. And that t equals 0 corresponds to looking like this. That's our r. And then our r prime, our velocity is that, and they are at a right angle. And you might be able to visualize that for any other point, then its movement is not at a right angle to the position vector. So indeed, that checks out visually. So we just have that t is 0. However, that's not what we input, because it wants the points on the parabola where they're orthogonal, not just the parameter value. So we know that this occurs only when t is 0. We plug that in. So we have that r of 0. Plugging in, we have that. 1, 0. Or regarded as a point, not a vector, that's 1, 0. That's it. That's the solution, just that one point. Here's the picture. That's our r of t. Our r prime of t looks like that, and they are at a right angle there. All right, that concludes this relatively short chapter, and have a great one. Next section, we'll wrap up chapter 14.